This is linear transformations. This is scaling and dilation. Now this represents a 2 dilation because it slips from 1 to 2. So we're just effectively making the area of this square larger by a scale of 2. Now this is an example of a linear transformation, and there are many more. And this is another example of KL scaling, where k equals 2, L equals 1/2, and it stretches this to this point here, which would be this here. And a rotation in our plane where theta equals pi over 4, and this is just this for r, a rotation of pi over 4. Now a k dilation in r squared, which would map k to xy to k xky, and a KL scaling of our plane maps xy to kx and ly, so which will be given here. Now a rotation matrix, which will be shown here, is also a linear transformation. So if we rotate from the points on this side to here, will give rise to these trigonometric components here, and this is our transform coordinates, which if we go through this process and then we're plugging in our value for a rotation of pi over 6a, we'll get this as our rotation matrix, which is our linear transformation. Now a definition: let v and w be vector spaces. A function t which maps v to w is a linear transformation if 1. T v1 plus v2 equals t v1 plus t v2 for all v1 v2 contained in our vector space. And second condition is t alpha v equals alpha tv for all v contained within our vector space and alpha contained within the reals. Now we'll find the matrix representation of this linear transformation as an example with respect to non-standard domain basis given here, and the non-standard codomain basis here. So we find images of the domain basis, and we find the f coordinate of each of these image vectors, where f equals these, which are here given. For the first image vector, we need ABC contained within our reals such that 2, 4, 1 equals ABCF. Now since ABCF equals A 1 1, B 0 1 1, C 0 0 1. So again we're just putting these together and equating and solving for A equals 2, B equals 2, C equals -3. So therefore our transformation of T11 equals 2 3f. Now for the second image vector, we need D, E, F contained in R such that 2 3 0 equals D, E, F, F. Now since D, E, F, F equals this here, and equating again, we'll get D equals 2, E equals 1, F equals -3, so we get this conclusion. So therefore this transformation is given here. Now hence the matrix of T with respect to basis EF is this. Thus the matrix representation of T with respect to non-standard basis E for our plane and non-standard basis F for our space is this. Now the inverse of a transformation. We find the inverse of T, mapping from the plane to the plane. So xy maps to x plus y 2y. So our answer T 1 0 equals 1 0 and T 0 1 equals 1 2 as our standard basis in our codomain. Hence the matrix is given as such. Now if we evaluate the determinant, we'll get which equals 2. Since it does not equal 0, this is invertible. So our inverse function we'll take a V equals our inverse A, V. Now our inverse A, as we should know from basic matrix algebra, this is our inverse. So equals this after multiplying out our 1/2. So it follows that T inverse as a matrix form given as such. And so our T inverse is the linear transformation given here. Now the kernel of a linear transformation. Let T map P3 to P3, and P of X maps Px plus P2. And I will let P of X be this here as a polynomial in P3, and we'll let our mapping be shown as such. Now the kernel of T is the set of polynomials in P3 that do not satisfy this condition. So for all x contained in the reals. So if we start equating these components with 0, and we're substituting b equals 0, c equals 0 into the first equation, we get a equals 0. So the only solution is here, where all the components are 0. Thus the only polynomial in the kernel of T is 0 polynomial. So our kernel of T equals 0, the set 0. So the kernel comprises only of 0 vectors, so dimension is 0. Now our dimension theorem, we'll let T be a mapping of V to W, be a linear transformation. Then dimension of our image of T plus dimension of our kernel of T equals our dimension of our vector space. Now as we'll show this, T, we're mapping from our space to our space as our reals, and we'll take this example here. So the image set of T in the is the xy plane, as we can see here. So dimension of our image of T equals 2. Now the kernel of T is the z-axis. So kernel of dimension of the kernel of T is 1. So dimension of our image of T and dimension of our kernel of T equals 2 plus 1 equals 3, which is the dimension of the domain of our space. So that's the dimension theorem. And that was linear transformations. Please do like and subscribe.